All right, hello and welcome back. Let's get started on chapter 10. We're going to talk about the constant E and continuous compound interest. Our first question is asking us to solve for P and round it to 2 decimal places. So we're looking for this P, and so to get a P alone, I'm just going to divide out anything on the right-hand side that isn't P. Right, I want to isolate it. So if I do that, I get P is equal to 57,400 over E, the 0.068 times 9. Okay, and so you can put this in your calculator as this if you want to simplify that power on E a little bit further. Okay, and in your calculator you should get 31,126.03. Remember, round to 2 decimal places. That's our p-value. Okay, so here we want to solve for what x is. So it doesn't exactly say it, but we want to know x is equal to what? So I have e to the 0.006x is equal to 35. Now, we can use properties of logarithms to undo this e, and whatever I do to the left side, I have to do to the right side. So if I take the natural log of both sides, we have a property of natural logarithm or logarithms where we can take this power and bring it in front. So I can rewrite this as 0.006x times the natural log of e is equal to the natural log of 35. Okay, and the natural log of e, they're inverses of each other, so this is equal to 1. So we really get 0.006x is equal to the natural log of 35, and then I want to isolate x, so I'm going to bring that 0.006 to the other side, like so, just divide it out, and if you put this in the calculator, we should get 592 point, and then we want to round to 4 decimal places, so 5580. Right. Okay, so here is a continuous compound equation where it takes on the form A equals P PERT, where A is the amount at the end of at time t, and P is your principal, E is our constant E that we're learning about in the section, R is the rate of interest, and T is the time that you're wondering about. So this first question we have, if T is equal to 2, what is my amount? So if I use 19,000 E 0.09, all I have to do is just plug in that 2 for T. So right here. And then the question wants us to round to the nearest hundredth. So if we plug this into the calculator, let's see, I got 22,747.13. Okay, and so we can continue on for the other 2 parts. Just plug in the times that we were given. So 0.09 times 4, this gives me 27,233.26. And for the last one, if I plug in 8 for T, I get 0.09 times 8, and this gives me $39,034. Oops, extra 0. $34.23. All right, so here's asking a different question, but still related. So we have a principal amount of $3,000 invested at a rate of 6.3%. We know that it's compounded continuously, so it takes on the form A equals PERT. Or we can write this knowing the numbers we have. E And then you always want to convert the R to a decimal. So 6.3%, you just move the decimal point 2 places. Fill in a 0 if you need. And so decimal form, it's 0.063. And then that t is our variable. So a is a function of t, which is suggested by its graph. Okay, so which one is it? So the p, our principal, is the amount of money that we put in at time 0. So at time 0, t equals 0, my amount should be 3,000. And we kind of verify this because if we plug in 0 for t, we get 3,000 e 0.063 times 0. Anything to the 0th power, this whole thing goes to 1, right? And so we get 3,000 times 1, which is this. So if we treat it like a function, we would have this point on the graph. So t is my input and a is my output, so I should get the point 0,3000. So let's find which graph has 0,3000 on it. So a has the point 0,0, right? That's not what we're looking for. This looks like it has 3,000, part B, so that's potential answer. So to C, right, this point right here is probably 3,000. Same for D. So all potential answers. E again looks like it's going through the origin as well as F, so I think we can throw away A, E, and F. So now between B, C, and D. So what else do we know about our function that I'll highlight here? So exponential functions are always increasing. I should never expect it to go downwards, right? Because the e of x, the graph of it, looks like this. So all we did here is we just added a constant multiple, so it's just a little more exaggerated. So I think that means that we can throw out c, because it has a downward slope. That means as time goes on, my amount actually goes down, which that doesn't make any sense, because if we have a compound interest, that means that I should have more money as time goes on. So we can throw C out, and so now it just comes down to B and D. And it's very slight, but D looks like a linear function, right? But B kind of has a slight curvature to it, which would suggest exponential growth. And that's where our special constant E comes in. It's not a constant increase over time. It actually will increase at a faster rate for longer t values. So that's why we have this kind of curve. It'll pick up very slightly in this case. So B is our answer. Okay, so for this question, we want to fill out this table. Shouldn't be too hard, I don't think. Really, we have this formula here, 1 plus 1 over n, and this whole thing raised to n. And all we want to do is plug in these n values here and see what output values I get. So you can do this on a calculator. It's probably going to be the easiest. And so I got, for n equals 100, I got 2.70481. And always read the directions about rounding, 5 decimal places. Okay, so we can continue. When n is 1,000, I got 2.71692, and then 2.71815. Of course, you'll be putting in your answers over here. For 10 or 100,000, I have 0.71827, 2.71828, and the last one's 2.71828. So So basically the goal of this exercise is just to show you that for larger values of n, right, as my n's increase, notice that my values, as we plug them in, they're starting to approach this number, 2.718, and a whole lot of change. And that's how we defined e. So we define e as the limit as n goes to infinity of this expression that you just used, and this equals e. It's just a little exploration about the constant e there for you. Okay, and then question 2. So this one's saying that it can be shown that this e can be between these two expressions when n is greater or equal to 1. And so we want to graph these 3 functions. And so basically, we first want to, I think the easiest one would be to graph y2 is equal to 2.7. So I believe each of these tick marks are 1. And so 2.7 would live around here. This is not right because I'm taking the horizontal as y2. So this is probably like 0.7, so y2 is equal to 0.7. So let's throw b out. I think c also might have y2 equal 2.7. So potentially c, and then d, again, we have this 0.7 perhaps. So probably throw out d as well. So now the difference between A and C is very subtle, but basically it shows y3 on top versus y1. And using this definition, we were given that this one is y1 and this one's y3 using these. So that means that E should be between y1 and y3, so y1 should be the one on the bottom. And so A is our answer. Okay, so a little bit of application questions with compounding continuously. Again, we're going to use our handy dandy formula, A equals P E R T. Okay, so it says if 50,000 is invested in this CD, how much will it be worth in 5 years? So let's unpack that. So we have this is invested, so that's our principal, so our P, that's the amount that we put in initially. This is our T, right? We want to know how much is it worth after 10 years, or sorry, 5 years. So T is equal to 5. And then up above, we actually also were given R. This is our rate at which it's being compounded. Remember that we always want this expressed in a decimal, so let's move that decimal place over 2 and fill any zeros. So I get 0.0263 as my decimal. And I think now we know enough to solve this question. So let's just plug in what we know. So A equals 50,000, put our constant E, and then that's raised to 0.0263 times 5, which is our time. So you can plug that right into the calculator and get A is about 57,026.90. We are rounding to the nearest cent, so just pay attention to that. For part B, we want to know how long, that sounds like a T question, right? How long will it take for the account to be worth 75,000? Okay, so we can use the 50,000 from above, because it's a continuation of it. So this was the amount that we originally put in, 50,000. We now know that or want to know when A is equal to 75,000, our worth after T amount of years. That's what we're solving for. And again, we can use the rate from above, so that's 0.0263. So let me plug that into my formula. Let's put these over here. So let's put it into our formula, A equals PERT. So now we have 75,000 on the left-hand side is equal to my principal, that's 50,000. my constant E raised to my rate of 0.0263 times T. And T is what we're solving for. So when answering these questions, you want to make sure that you only have one unknown, because that'll make solving for these variables easier. So in the first question, we had only A as an unknown, and then in this question, we only have T as an unknown. So that's an important step, that you have only one variable to solve for. Okay, so let's solve for T. I'm going to first divide out that 50,000, so let's move that to the other side. Let me put 75,000 over 50,000 is equal to E to the 0.0263 T. All right, but I still want T alone, so how can I further simplify that? Any ideas? Remember, I don't know, one of the first few problems that we can take the natural log of both sides, right? Because we know a special power about logarithms. So if I do that, remember that I can pull this power down. And that's going to help us tremendously. So I still have the natural log of, natural log of 75,000 over 50,000. And so if I pull that power down on the right-hand side, I get 0.0263 T times natural log of E. Remember, natural log of E is just 1. Okay, so I'm going to continue this up here. So I want to further isolate this T, should be our last step. I'm just going to divide that rate over to the other side. And so I get T is equal to the natural log of 75,000 over 50,000, and then divide it by 0.0263. And so where do we want to round? To 2 decimal places. So my T, if I put that in the calculator, I get 15.42 years. And that's our answer for part B. Okay, let's do one more. So a promissory note will pay $60,000 at a maturity of 7 years. So that sounds like time, so that'll be our T. Now, how much should you be willing to pay for it now? What does that sound like? So P, if the money is worth 6%, and usually that's our rate. And then I glossed over the 60,000 because usually you have to decide, is this number your principal or is this your amount? And so here, this is our amount at time T. So that's our A. And so we know everything except for P, and that's what we're solving for. So let's make our formula. A equals P E R T. We're compounding continuously, so we'll use this formula. 60,000 equals P. We don't know what that is. That's what we're solving for. The constant E, our rate as a decimal. Remember how we do that? Move the decimal point over 2 places. So 0.06, and then T is 7. So this is kind of like the first problem where we solve for P. So all you do is you divide all of this to the other side and get 60,000 over E to the 0.06 times T, which is 7 here. And so if we put this in the calculator, we have to round to the nearest dollar, so that will be $39,423. Okay, so let's do some half-life and decay questions. So we have a radioactive element that decays according to this function here. Q naught is the amount at time 0. R is the continuous compound rate of decay. T is the time in years, and Q is the amount of substance at time T. It's kind of similar to our A equals PRT, right? In this case, Q is our amount at time T, and Q naught is the amount at time 0. So very similar. But anyway, we know that our rate here is this decimal. So notice it's not a percentage, so we don't have to convert it. And then we want to know how long will it take for a certain amount of this element to decay to half of its original amount. And then this is called the half-life of its substance. So in the other questions, we were given an A, a P, well, we knew E, and then RT, right? But here, we're really missing the Q and the Q naught, because we know what R and T is. But I'm going to say that we don't actually need to know what Q and Q naught are, because we can use a little fact that they told us is that we want to know what its half-life is. And so this means at a certain time T, at its half-life, we expect the amount to equal 1/2 of the starting amount. So this is our amount at time T of our half-life, and this was the starting amount, so our amount is 1/2 of Q naught. So we can use that, right? And then if we use that in our formula, Q equals Q naught ERT, I just got that from up here. So now I'm going to plug in what I know Q is and get 1/2 Q naught equals Q naught. Let me plug in the rate. That's negative 0.000365 T. And notice that my Q naughts, they kind of cancel out, right? If I divided them from both sides, they cancel out. So it really didn't matter what Q or Q naught was. And so I get 1/2 equals E to the minus 0.000365 T. I'm solving for T here. So to isolate it, let's do that natural log trick. Whatever you do to one side, you have to do to both. Then I'm going to pull this power down, take the negative with it. So I get natural log of 1/2 is equal to minus 0.000365 T natural log of E. What is the natural log of E? That's 1. And so to solve for T, I'm just going to divide out my rate. So T is equal to natural log of 1/2 divided by the rate. That's this piece here, so minus 0.000365. We are rounding to the nearest year, and so I got 1899. Okay, let's do one last problem. It's kind of similar. Again, we have this formula, Q equals Q naught ERT. I believe, let's see, all the variables mean the same as the last problem. Yep. And so an isotope has a half-life of 93 years, and we want to know what is the continuous compound rate of decay. So let's see. So if we use our Q equals Q naught ERT, we know that our time is 93, and we know that it's a half-life. So half-life means at time 93, I will have 1/2, the amount will be 1/2 of what I started with, Q naught. It's kind of like the last problem, remember? So I'm going to use this relationship right here and this T value to substitute in 1/2 Q naught equals Q naught E. We're solving for R, and my T was given as a half-life of 93 years. So again, if I divide out my Q naughts, they cancel, which is great, because then once they cancel, I'll only be solving for R. So 1/2 is equal to E93R. Let's take the natural log of both sides. Now I can bring this 93R down. So I get natural log of 1/2 is equal to 93 r natural log of e. One more time, what's the natural log of e? That it will be 1. And so to get r alone, I'm going to divide both sides by 93 and get natural log of 1/2 over 93. And so my rate of decay is negative 0.0075 rounded to 4 decimal places. And that will be my answer. All right, so hope this was helpful, and I will see you in the next section.